Hi folks, today we're going to introduce the exponential parent function. So the exponential parent function is f of x equals, and because it's exponential, the root word of exponential would be exponent, so we're going to have an exponent in there. In fact, our variable x is going to be our exponent. So we're going to take some base, b, we're going to raise it to the power of x. This is our exponential parent function. So we're going to use base. We're going to use a base of 2 whenever we're creating our table of values. That way we know what it is that we're raising to the power of x. So over here in our table, we're going to use a b of 2. So we're going to raise 2 to all of these powers. Now, whenever you have a power of -3, so 2 to the power of -3, remember your exponent rules. When you have a negative exponent, what that means is that you take the negative exponent and its base and you kind of flip it into the other part of a fraction. So if it's not in a fraction right now, then you say it's in the numerator. And if you flip it to the bottom part of the fraction, now it's in the denominator. So 1 over 2 to the power of +3. And 2 to the power of +3 is 2 times 2 times 2. Well, 2 times 2 is 4, times another 2 is 8, so this y value is 1/8. So we're going to do the same thing with a power of -2. So I'm going to raise 2 to the power of -2. What this means is that I put the 2 to the power of +2 in the denominator. And 2 squared is 4, so I have 1/4. So what I'd like for you to do is pause your video and continue taking a base of 2 and raising it to the power of your x over here in this column and getting your y values out of it. So pause your video and finish the table. So this is the completed table. Remember that whenever you have 2 to the power of -1, you put 2 to the power of +1 in the denominator, and 2 to the power of +1 is just 2. So we have a y value of 1/2. And the other exponent rule that it's important to remember for this table process is anything to the power of 0, anything at all, is going to be 1. So 2 to the power of 0 is 1, and we get a y value of 1. So now we have 7 ordered pairs, an x and a y value together, that we could graph. And so what I'm going to do for the sake of graphing on our video is I'm going to take these ordered pairs and I'm going to rewrite them down here on the graph, just so that I have my graph and my ordered pairs together on the screen at the same time. So -3, 1/8, -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. So now I can graph these. I can figure out what the graph of the exponential parent function looks like. So when I graph these, remember that the fractions 1/8, 1/4, 1/2, that's going up just a little bit, and we're not going up a full unit. So -3 and then 1/8. So there's -3, and then I'm only going up 1/8. That's going to look like it's resting on that x-axis. -2, 1/4, not much higher. -1, 1/2, about halfway up. 0, 1, 1, 2, 2, 4, and 3, 8. So this is a curve. I'm going to go ahead and curve it up. Just like that. It'll keep going, and then I'm going to curve it down. Now we'll notice that it's getting really, really, really close to the x-axis, to y equals 0, but it's not actually touching. In fact, anytime I have a really negative number, and I raise 2 to the power of a really negative number, it becomes 1 over 2 to the power of that number. And so we're just going to keep getting fractions, but the fractions are going to get smaller and smaller and smaller. However, they're never going to become negative. And so what that means is that here we have an asymptote. We don't have one here because it's going to keep going out and out and out and out, and we'll be able to use new x values. But here it flattens out, and it's never going to cross that threshold of y equals 0. So, some key attributes of our function. The b, the base, will be greater than 0. Okay, so we'll always have a base greater than 0, and b can never be equal to 1, because let's look at what would happen if we raised 1 to the power of all of these x values. Well, 1 to the power of 3 is 1 times 1 times 1. That would just be 1. 1 to the power of 2, that'd be 1. 1 to the power of 1, that'd be 1. 1 to the power of 0, that'd be 1. 1 to the power of negative 1, that would be 1 over 1 to the power of 1, and that would just be 1. So we're still getting 1s. 1 to the power of negative 2 would be 1 over 1 to the power of 2. That's still 1. So b is never going to be 1, and it's never going to be negative. The domain, from left to right, I don't have a boundary over here, and I don't have a boundary over here, and there's no holes or asymptotes that are vertical, so that means my domain will be all real numbers. The range, the y values. Remember, the y values never cross that threshold of 0. So if they never go down here, that means that they're always positive, so the y values are always greater than 0. The x-intercept. Well, I notice that it's never crossing the x-axis, and that's because there's an asymptote here. So there is no x-intercept. But there is a y-intercept. In fact, the y-intercept is the same for the exponential parent function no matter what base you use. So the y-intercept is located along the y-axis. That'd be right here. That's the point 0, 1. That's because any value of your base that you raise to the power of 0 will always be 1, because that's an exponent rule. So anything to the power of 0 will be 1, and we'll get this y-intercept. The vertical asymptote, well, there isn't one. And we're so used to hyperbolas, maybe we think there's one right here, but there's not, because I can raise 2 to the power of 4, and I can get 16. I can raise 2 to the power of 5, and I can get 32. I can keep going and keep moving to the right on my x-axis. So for a vertical asymptote, there's none. There is none in an exponential function. But there is a horizontal asymptote, so we talked about how this graph kind of flattens out along the x-axis. That's a y value of 0. Our y values always remain positive. The range is all the y values greater than 0, so there is a horizontal asymptote. And it's at y equals 0. And finally, let's discuss the end behavior. So we have two ends of the graph, and we'll discuss this one first. So as x goes to what? If x is moving this direction, then it's approaching negative infinity. So as x goes to negative infinity, y goes to what? Well, what's happening? The graph is coming down, it's going to the left, and it's never stopping, but what's it getting close to? What y value is it getting close to? It's getting close to 0, right? It's getting close to that asymptote. So as x goes to negative infinity, y goes to 0. And the other direction, as x goes to positive infinity, y goes to what? Well, that would be this direction. So as x goes this way, the graph is going up and 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 up, and it's never stopping, so it's going to infinity. So this is the exponential parent function today. The equation is f of x equals a base to the power of x. We used a base of 2 to generate a table of values. We took those values, we created ordered pairs, and we plotted them on a graph, recognizing that we had some kind of asymptote, some kind of horizontal asymptote. And then we have a list of our key attributes.